Great, Michael.
Okay, thank you. So I want to talk about algebraic circuit lower bounds, and if you have such lower bounds, what do you get in terms of derandomization? This will sort of be a vignette of recent work. It's not going to be like the latest and greatest, but it's something which is a nugget which I hope you can take away. It's going to be sort of taking these algebraic circuit lower bounds, making them robust in some way, and say that they're sort of immediately gives some derandomization. So this is based on some various joint works with the Mirishpilka. Okay, so what is the theme of this talk? It's this question sort of surrounding this workshop, so is that if you have some circuit class, you have a lower bound for that circuit class, what does that give you in terms of algorithms for deciding properties of circuits from that class? And what I want to focus on here is I actually want to focus on deterministic algorithms, in the sense that here, the properties I'm interested in, there will be automatically easy randomized algorithms. The question is, can you de-randomize those algorithms? So why am I asking this specific version of this question? Well, clearly I want to de-randomize some algorithms. But more broadly is that there is this idea that you can take lower bounds and de-randomize things based on in this hardness versus randomness paradigm. But oftentimes, the circuit classes that we'll be interested in are just simply too weak to instantiate this connection. So we really have to answer this question by looking at those lower bounds fresh. Right? And there's some idea that really, understanding these lower bounds in a way is really, to get algorithms is like the best way you can understand lower bounds. You don't really understand them until you get an algorithm. Okay, so I want to talk about lower bounds and algorithms from them. But what are these properties I'm trying to decide? Well, the main property is that of non-zeroness. So there's this polynomial identity testing question. What is this question? I'm giving you a polynomial. It's going to be multivariate. It can really be over any large enough field that you want. I'll just stick to the rationals for this talk. You're given this polynomial, and you want to know, is it zero or not? Okay, so it's a very simple question. But the main subtlety in here is, what does it mean to be given a polynomial? I mean, there's many ways to get a polynomial. You can get it in the mail. You could get it via email. I don't know. But when I mean to be given a polynomial, I'm going to give it to you as a small computational device. Okay, so for example, you can consider x squared minus y squared. You could factor it as x plus y times x minus y. And I want to say that I'm sort of giving it to you in some computational way. And how is that? It's by a formula as follows, right? So this is a tree. You have sort of variables at the bottom. You have scalars from your field. You have addition and multiplication. And if you have an object like this, this naturally computes some polynomial. So what I could do is I could, have formulas like this. I could send it to you via email. You'd be getting a polynomial. You want to know, did you get some non-trivial email? You want to know, did I send you a zero polynomial or not? That's the polynomial identity testing question. Okay, so this is the question. This is the property I'm trying to decide of a given circuit class. What do we know about it? Well, there's this well-known lemma due to Schwartz and Zibel that says that if you have a non-zero polynomial, it's non-zero if and only if you have its non-zero evaluation points for random evaluation points. Okay, so this easily gives you a randomized algorithm for deciding non-zeroness. You get one of these formulas. You just plug in random values to the variables, and you evaluate the formula. You want to know, is that corresponding evaluation point 0 or not? So that's a very easy randomized algorithm. And furthermore, it has the property that it's black box, in the sense that you don't actually need to look at the formula and understand the structure of how it's actually wired. You just need to use the formula to evaluate the underlying polynomial and see if that evaluation is 0 or not. So we have a randomized black box algorithm, and we want to know, is there a corresponding deterministic algorithm? And in particular, we want maybe a deterministic black box algorithm that only uses evaluation points. I mean, you can imagine other algorithms, but for this talk, let's stick with the black box. And in this case, the equivalent notion here is something called a hitting set, which is, as I said, equivalent to black box PIT. A hitting set is a set of tuples. It'll be a set of input points, sort of curly h, and has a property that for any small formula, so any computationally simple f, that polynomial will be 0, or correspondingly non-zero, if and only if it's non-zero on the evaluation points. So the runtime of your algorithm is really corresponding to the number of evaluation points in your hitting set. So you want a small set. And because we're restricting to simple functions, we know that there exists very small hitting sets non-constructively. And the question is, can you algorithmically construct one of these hitting sets? Okay, so this is the property I want to decide. You have some circuit class. Decide whether it's non-zero via this sort of hitting a set approach. But then the question is, what is the circuit class I want to talk about? There's many different types. What I want to tell you today is a very simple type. It's called the depth repowering formulas, which is not super familiar to many of you, but I'll tell you about it anyways. Okay, so in algebraic formulas, typically when you compute polynomials, you use things like addition and multiplication. But it's a very familiar thing to change your gate set. So what are other gate sets that are natural in this setting? Well, you consider addition and powering. Okay, so you can take xy, that's a multiplication, x times y, and you can actually express it as the difference of two powers, x plus y squared and x minus y squared. And so it's saying that in terms of gate sets, addition and powering is the same thing as addition and multiplication, so for general formulas. But the problem is that if you actually try to do this for, say, low-depth formulas, this equivalence breaks down you can do it. So it's not going to hold for low depth. So the question is, what happens when we restrict ourselves to low depth powering circuits? Specifically, we talk about depth repowering formulas. these turn out to be something called the sums of powers of linear forms. So if we write it out, we have a polynomial f of x. It's going to be x1 up to xn. We're going to have a big summation gate, sort of s things here. And then we take a linear form, and we take to some power. And we're sort of thinking of this power as maybe like polynomial in n, like n squared or 10 or anywhere in between. And we have these constants coming from our field. So you have a sum of powers of linear forms. And I think for most people, you ask yourself, why are we studying this? And I ask myself that sometimes too. But there's some question that this is actually a very fundamental model in the sense it's a sort of a moral analog of CNFs and DNFs. It's very, very simple. It's very, very weak. And yet it's sort of, we still don't fully understand it. As Parikshit mentioned yesterday, we don't have optimal pseudorandom generators for DNFs. We don't have optimal hitting sets for this model either. And this is sort of an obstacle to understanding further progress on larger models. Okay, so it really, this is the intersection of many techniques, and we still don't have a good understanding. But we do have some understanding. What understanding do we have? We have lower bounds of this model. So what is one lower bound? It's the following. Consider the monomial. It's x1 times x2 up to dot, 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 xn. This actually requires exponential size to be computed as a depth repowering formula. Now, in some sense, this is embarrassing because the monomial is, in some sense, a very, very simple polynomial. In some sense, it's sort of like parity if you think about it in terms of the plus minus 1 basis. So there's some analog with, say, parity not in AC0 here. But this monomial takes exponential size as a lower bound. There's also a corresponding upper bound. These depth repowering formulas can compute anything. So this is lower bound. It's even for the monomial. I mean, obviously, it applies to things like the permanent, indeterminate, and so on. So this is what we know. It's basically proven by this partial derivative method of Nisan-Wigderson and sort of explicitly noticed by Kyle. One thing I learned here when I was at Simon's last year is actually this is actually known to mathematicians in 1850s. So it does have a illustrious history. But this is lower bound. But what does it tell us about, say, deciding non-zeroness? Well, the result I sort of want to tell you about today is the following. Suppose I give you one of these formulas. Now take it and express it as a polynomial. Like just expand all of the monomials. There are going to be many, many monomials. And this polynomial will actually be determined by its restriction to those monomials on very few variables. So let's parse this for a second. There are many, many monomials here. If the monomial involves more than, say, log s variables, just throw it away. Just like zero out that coefficient. You'll be left with a sum of monomials where each monomial involves few variables, which variables might depend on the monomial. But you'll have very, very few monomials. You'll have a quasi-polynomial many monomials left. And I'm saying those coefficients actually determine the function. So this is some sort of structural result sort of corresponding to like lineal Mansour-Nissan's result on AC0 about Fourier concentration. It's like some algebraic analog. Okay, so it's saying that f is determined by these sort of very few monomials, and you actually can easily get a hitting set of quasi-polynomial size based on this. Okay, so this is a structural result giving hitting set. And how do we actually prove it? I want to sort of tell you about it today. It's basically by taking this lower bound and making it robust in some way, which is actually fairly easy in retrospect. Okay, so I want to tell you about this now, but to do it, I need to tell you about the lower bound. How does that go?
So does the size refer to the first sum or the second sum?
Sorry?
Or both? Oh, only the second sum.
And then,
what does the S mean in size S?
So S is the number of summations you have here. So there's sort of various parameters. D will sort of be polynomially bounded. S could be anything from 1 to exponential. And the number of variables will always be n. All right, so here's how does lower bound go? It's a sort of familiar path. It's something called a complexity measure. It's some measure that you can assign to any polynomial that is roughly corresponds to how complicated it is. So what is the measure that we're interested in here? It's this partial derivative method. So you have a polynomial. It's n variables. And what we're going to do is, because it's sort of over the rationals, you can think about taking derivatives, right? You can kind of remember calculus. You can take derivatives of polynomials. And when you take a derivative of a polynomial, you get another polynomial. Okay? What you're going to do is you're going to take all possible derivatives all possible ways. So take the xn variable and take the differential with respect to an times. Look at the x1 variable, take it a1 times. You do all of these derivatives, you're going to get an exponentially large set of polynomials. You take that set, and then you take all linear combinations. This is now a vector space. And you take a dimension, and that's the measure here. It's not super important what it is at the moment, but this is the complexity measure. And what do we know about it in terms of facts? Well, it's pretty easy to see that it's subadditive because this is linear algebra. Linear algebra is magical. But more importantly, we can actually say that if you have a power of a linear form, then the measure is small. Okay, so why is this? This is roughly because of the chain rule, right? You have this linear form, and you take it to the dth power. What happens when you take one derivative? When you take one derivative, the d will sort of pop down. The exponent will go from d to d minus 1. And then you'll multiply by a derivative of the inner function. But the point is that a derivative of a linear polynomial is simply a constant. Right? So what will happen is when you take a derivative, constants will sort of pop out. The exponent will decrease by 1. But the point is that we're taking the dimension of a span. And so you're just basically you're ignoring constants anyways. So from the perspective of this complexity measure, when you take a derivative, all you're doing is decreasing this exponent by 1. So the space of derivatives is simply the powers of this single polynomial where you go from d to d minus 1 all the way down to 0. You get d plus 1 of them. That's why this measure is small. Okay. And then you can sort of expect what would come next is that the measure of the monomial is very, very large. Right? So if you take a monomial and take a derivative, it basically just kills that variable that you took a derivative to. So basically, when you take all derivatives, you get all subsets of a universe of size n. There are 2 to the n of them. That's why it's 2 to the n. Okay, you combine these 3 things, and you immediately get the lower bound, that the monomial needs exponential size to be computed this way. Right? You apply mu to both sides, you use subadditivity, and then each of the summands has small measure. Okay, this is assuming that the exponents are small, but you can sort of remove that with another argument. Okay, so this is the lower bound. You can see it's like fairly simple, and obviously, it can be generalized in a lot of different ways. The question is, how do we actually use this to get identity testing? How do we, you're given one of these formulas, you want to know, is it 0 or not? Okay, so we were going to make this robust. To do that, let's try to understand what a lower bound is telling us. What a lower bound is telling us is if I give you a small formula, you immediately know it's not computing the monomial. Because if it was computing the monomial, it would violate the lower bound. So that's telling you something about the polynomial. It's not necessarily telling you whether it's 0 or not. But can we push this in some way? Well, one way we could try to push it is there a way in the sense that if I give you one of these things, can it approximately compute large monomials? If it could not approximately compute monomials, maybe that would tell us something more. Well, let's do an example. Right, if we do an example, we have power of this linear form. And when you expand it out, you immediately get this really, really large monomial. And that seems to be problematic because, maybe in some sense, this linear form is approximately computing this large monomial, which would refute, this question or something like that. Okay. But it turns out that the answer is really no, and that's because there is other stuff going on here. There are other monomials like x1 to the n, xn to the n. And I want to say that those are ruining any sense in which this linear form is computing approximately this monomial. So how can you make that precise? Well, you do the following. Suppose I give you a non-zero polynomial, say computed by one of these formulas. What you're going to do is you're going to take f and express it as the leading monomial plus lower order terms. And how do I make this distinction between the highest term and the lowest term? You can take a monomial and you can order it lexicographically by doing the following. You take the first variable, x1, and you say that's a really, really big variable. And then x2 is slightly big, but slightly smaller. And then xn is the smallest variable. And when you order all of these monomials lexicographically, you can this gives you a total ordering of monomials. You can very clearly see what is the leading monomial. And if you go back to this example, what is the leading monomial? It's not this big monomial. It's x1 to the n, because x1 is so big based on this ordering. Okay. And so now we can say, what is the robust lower bound? We can say the fact is that the complexity measure I just defined for you has the property that for any f, the measure of f is at least the measure of the leading monomial. Okay, so it's robust to these lower order terms. Right? You can sort of throw away these lower order terms, which you kind of think of as like error terms or something. Okay? And once you have this robust framework, you get the immediate structural result by applying the lower bound that says that for any small formula computed in this model, the leading monomial must involve very few variables. Okay, and then if you push it a little bit, you can get the structural result I mentioned in the last slide. But the main point is that you take this leading monomial bound on the number of variables, and you immediately get this hitting set. Okay, so this is how you make the robust things. You take a lower bound, you make it robust, and you get a hitting set. More generally, what's really going on, I can now conclude with some conclusions. A robust lower bound is basically something where you take a polynomial and you identify some extreme aspect, something like a leading monomial. You have a complexity measure where it happens to be that mu of the extrema plus lower order terms is at least mu of the extrema. And you can conclude from that the extrema must be very, very simple. Now, this seems kind of restrictive in the sense that leading monomials, we really use the fact that the lower bound was for a monomial. And that seems to be important, but there are other instances of this. Some various other works that have used this idea are the following. But this is still sort of an emerging theme in this area of research about taking lower bounds, making them robust, and getting algorithms out of that. And there are still some open questions. Open questions which I really like is there a polynomial size hitting set for these formulas? They're so weak they can't even compute the monomial, but we still don't have a full understanding of them. We don't know the answer to this question. The best result is s to log s for size f's formulas. Anyways, I'll stop with that. Thanks.
What would be an example of kind of a hard, reasonable hard function that computes by this class of polynomials?
The answer is yeah. I mean, there's not really anything that's hard that's computed by these things. I mean, they can compute small monomials. I mean, basically you can, yeah, they don't really. So I can tell you that they have actually come up in Katan Momoli's papers on the so-called nether normalization that he's been doing. He really wanted actually identity testing exactly of this model because he was doing invariant theory for the special linear group of constant size matrices, I think. So that came up there. But I think the main reason that we study this is basically because there are various techniques that go on, and this is sort of at the intersection of every technique that works in algebraic complexity, and yet we still can't understand them.
Can you get the Rashid identity test for non-commutative APPs directly from Nissan's lower bound this way?
Okay, so obvious question is like there are these things called non-commutative APs, and there's a white box identity test for these things, which is here I talked about black box where you're really using evaluation points, but you can generally ask, what if you really look at the structure? And Rajan Spilka gave a polynomial time algorithm to decide that, and actually that algorithm actually does give polynomial time for this model also. So if I give you one of these things, you can actually decide in polynomial time whether it computes the zero polynomial, but you're not necessarily using evaluation points. But I think the answer is basically no to your question. Like you can't. I mean, this robust lower bound idea seems to work well in the black box case, white box case.
Let's